Would you like to see something before we start? Why not? Do you mind if the video, if you're on? Shut up, Bashir. Okay. Anyway, I just want to, we're talking about acids and bases, and this lecture does not take the whole time. So I'm not going to do that thing where I'm up against the bell. So I just thought I'd show you something kind of interesting about acids and bases. You know what happens? We talked about it last year. You know, if an acid and a base mixes together, it's neutralization, and they cancel each other out ultimately. So I wanted to show you something cool about essential water. There's a bunch of items that are like this, where it's water that's sold as alkaline. Do you know what the word alkaline means? Let me read to you what alkaline means. pH quality guaranteed, 9.5 pH or higher until opened. It's basic. pH of 9.5. Basic water, it has some health benefits if you're drinking basic water. So I just thought that we could prove it true or not. So what I did is I poured. Oh, I forgot my straw. Hold on. Okay. So what I did is I poured some of the water in here. See the water? So I was just gonna drink the water for you, and then we'll start lecture. I'm just kidding. It's just some water. All right. Now what I also have here is phenolphthalein. Phenolphthalein is an indicator that turns pink in the presence of base. You're actually going to be using phenolphthalein in a lab next unit when we do titrations. So let's see if the pH really is basic, first off. So I'm just going to take a little flake of this, and we'll check it out. Are they really selling us basic water? Yeah. They are. All right, so they're on brand. That's good. So here's another kind of cool thing, though. What did I tell you was true about carbon dioxide yesterday? That it's acidic, right? The stuff that I'm breathing out is acidic. So wouldn't it be cool if I took this basic water and added some acidic gas? Let's see what'll happen. Now, be patient. In case it gets splashy. Okay, are you ready? I'm going to try to make you be able to see it and my people at home. All right, patience. Here we go. Any changes yet? You think this is going to work? It's going to be my last breath. This went fast the last period. Y'all having fun? Here we go. Ta-da! We neutralize the alkaline water with acidic human gas, which is kind of weird. But anyway, just a cool demonstration to show acids and bases, kind of like real world stuff, interacting with one another. So go buy yourself some alkaline water. Hey, I do want to mention though, interestingly, let me reread that label to you. pH quality guarantee, 9.5 pH or higher until opened. Why do they have to add that until opened designation? Moment you open it up, there is CO2 in the air, and at a much slower rate, it'll do what I did. Anyway, welcome to lecture 2 of our acid-base unit. Make sure you have your slides ready, called Advanced pH calculations. Yesterday, we revisited a bunch of honors acid-base stuff, basically. We remember how negative log works, remember how the pH scale functions, we remember what Bronsted-Lowry is, and all that fun stuff. We also introduced KW, which was new, a little splash of equilibrium into acids and bases. Today is different, all right? Stuff that you haven't seen. But before we get into some different ways to calculate pH, I do want to mention that when my test comes on November 11th, or when the AP exam comes, you are hoping that all the samples that they give you are strong. Strong samples are easier to analyze than weak samples. Like, look at those questions on the board right there. What do the two questions have in common besides the fact that they ask for pH? They're both strong, right? I bring clay is on the top one. Group 1 hydroxide's the bottom one. When it's a strong sample you're analyzing, that is great news for you because it's just negative log. Last year, all you did was this negative log calculation because everything we gave you was strong. We didn't make a big deal about it. We just didn't give you weak because you weren't equipped to solve it. But let's do the very bottom one. Look at the second problem. Calculate the pH of a strong base is ultimately what it says. And since it's strong, we can just go negative log of 0.71. And that will spit out a value of, which I hope you're clicking behind the scenes, but it gives me a value of 0.049. I'm sorry, 0.14. What is that number? It's POH. You've got to be careful, right? If you take the negative log of a base, it says KOH. Well, that spits out POH. Right? The question, in this case, wants pH. So even though this is an easier question because it's strong, so it's just negative log, there's an extra step there that you want to make sure you're aware of, where you subtract from 14 to get 13.851. And there's your answer. The other question that we skipped is the exact same thing, but without the extra step, right? Because it asks for pH and gives you an acid. Those things talk to each other, right? If it had asked for POH and given you a base, there wouldn't be the extra step. But it gave you a base and asked for the acidic trait, so it had that extra step. So be aware of that. That's all last year's stuff. Today is dedicated to weak samples, which you've never done before. If you're asked to analyze a weak acid or base, we're going to marry some of our skills together. One of the things is a rice table. If you have a weak sample, it is going to go in a rice table. Not only that, it's going to be added to water in a rice table for us to do our pH analysis. The interaction in that rice table will be Bronsted-Lowry from yesterday. And then finally, I'd like to remind you that liquids, like the water in these equations we're about to work on, are not considered for equilibrium, which is what rice is going to do. So, with all of that said, we're going to do 3 problems today. Each one gets 1 step longer each time, so the problems are just going to get worse as the day goes. But my point is to show you the 3 most common weak pH analysis questions that College Board will give you in May. You ready? It says, calculate the magnitude of the equilibrium constant. So it wants K for benzoic acid. Now, you don't know a lot about benzoic acid, but look at the formula. All right, it's Arrhenius. It starts with H, right? So we know it's an acid. Weak or strong? How do you know it's weak? It's a carbon-containing acid. The moment you're going to do any kind of pH analysis on a weak sample, you add it to water in a rice table. So let's do it. Let's take our benzoic acid, C7H5O2, and add it to water. Equilibrium arrow, because it's weak. Bronsted-Lowry interaction. Bronsted-Lowry says that the acid wants to get rid of a proton. So we need to remove an H+, which will make him look like this. One less H, one less plus. The amphoteric water is acting as a base, so he will accept the proton. So if you add an H+ to water, he becomes hydronium. One extra H, one extra plus. How are we so far? All right. The water in this type of analysis is always liquid and therefore ignored. I is the initial concentration. If you look at your data, it's 0.1. And we have no data for those theoretical products. The change shift down by the coefficient X for the reactants, shift up for the products. There are no coefficients here. Equilibrium, I plus C equals E. Join them together. Now, if you were okay last unit, then you feel really good right now because this is just a simple rice table. But we need a sprinkle. We know that we can't move forward unless we have other data. And now we've got a chunk of data that we've never had before because the question gives us a pH of 2.59. Remember, the best case scenario with the sprinkle is that we can identify X. Because if we can identify X, we can figure out what the equilibrium data is for everything and then plug it into our K expression and be done. And it turns out we do have enough info to find X. We were reminded yesterday that pH talks directly to one of those four substances. Which one? H3O plus. So who remembers? How do I turn a pH into hydronium concentration? 10 to the negative pH. All right, so that's in your notes from yesterday. If you go 10 to the negative pH, in this case, it will give you H3O concentration. Since you're doing it to a pH, that's what it always gives you. And when you run that, I get 1.3 E negative 3. And what's magical about that number? What is that number ultimately? Oh, sorry, but am I on the wrong one? Oh, 2.6 e negative 3. I chopped it in half for some reason. Is that a better number? My bad, my bad. We found X because we found hydronium. And look, it all lines up. So track your work carefully because it's a bummer to do the numbers right and then forget what you just found. Yeah, it's always because these X's are identical to each other. Yeah, they're all identical variables. Yeah, so now I have everything. So let's find K. Hey, let's start with an unsubstituted and be good little chem kids. So let's go K equals, but hey, look here, look here, look here. We're not going to just call it K. We've got fun little symbols. Hey, as a reminder, what does KC, what does the C stand for in KC? Concentration. What does the P stand for in KP? Pressure. What does the W stand for in KW? Water. All of those Ks are exactly the same. They measure the exact same thing. The little letters just tell you the environment that you're measuring. So since this is an acid, let's not call him K, let's call him K A for acid. But it's just a K. Products over reactants, raised to the power of their coefficients. So I'm going to take the products over, and by the way, I hope you're like going down with your work. I'm kind of wrapping on top of myself because my spacing is weird. But anyway, over reactant. Stop me if you don't like something. Substitute. We know the substitution is always the E row, but remember, I know X. So it'll be Ka. All right. The first product is X, so that's going to be 2.6 e negative 3. The second product is also X, so 2.6 e negative 3. The reactant is 0.1 minus X. Oops. But so sub in the F. So get there. Watch your order of operations, though, right? If you put some extra protection in those spots on your calculator, because a singular function is what you want, it'll protect you. I get a Ka of 6.9 e negative 5. No units on K because it's an equilibrium K. The conclusion would be that it's favored towards the reactants. All of that stuff exists. How are we doing? All right. So remember, each question just kind of has one more step hidden within it. So let's look at another. Calculate the magnitude of the equilibrium constant. So it wants K again. But there is a tiny difference this time. It wants us to analyze the ammonia. What do we know is true about ammonia? Weak base, though, right? Weak base. So since it's not strong, we cannot just go negative log. To analyze anything doing with pH, add it to water in a rice table. The formula for ammonia, as you've learned, is NH3. Let's draw some cards this time. It'll be fun. Let's go talk to cluster 2, seat 4. Hey, 2-4, what does ammonia look like after Bronsted-Lowry? NH4 plus is correct. He becomes ammonium because we know that bases are proton acceptors. So we added an H plus. Let's go over to cluster 6, seat 5, Aspen. Where are you at, Aspen? Hey, Aspen. What does water look like after Bronsted? Negative. Yep, pass the bird. OH negative. Because my amphoteric water is being an acid and giving away an H plus. All right, let's analyze the rest of this. The ammonia has an initial at 0.1 again. We're being nice and boring. And we've got nothing initial about these dudes. Track your change in the way we always do. You should be good at this by now. I plus C equals E. We all right? Let's look at the sprinkle. Look, it looks like the same problem. It gave us a pH. That's what it gave us last time. But here's where the extra step lives. And in this one, it's a really easy extra step. In the last problem, pH spoke directly to one of the things that was there. This time, it doesn't. pH doesn't talk directly to one of those, but there's something else that does. What do we need here? POH, because POH can talk to him, which can give us X. And we know that to get POH, it's super easy, since they add up to 14. Therefore, it must be 2.87. Now the rest is very the same. In order to turn that 2.87 into a useful number, we know that from yesterday, if you go 10 to the negative POH, it'll give you a hydroxide concentration. Ten to the negative 2.87 is the accidental number I wrote down last time because I was looking at the wrong place. But I get 1.3 E negative 3 molar. Which, of course, is X if you just track the info. unsubstituted. So we'll start with K. Ooh, what should I call this one? K. Yeah, look at that. We're analyzing a base. So let's call it KB for base. Products over reactants. Substitute, I'm going to draw a card for the answer. Remember, our substitution is the E row. I'm going to shorthand this just a tad. You can make yourself look smarter if you realize that it's x times x, which is the same as squaring it. It's less writing, right? X times x is the same as this times itself. If that makes you lose sleep, then you can keep them in their own brackets. But yep, like that. I mean, you can put those extra protections around it if you want to. And then over the reactant is 0.1 minus x. Let's go talk to someone. Let's go over to cluster 4 and talk to seat 1. Hey, 4-1! You were so excited to get rid of the bird. Do you have an answer? How many of y'all got that number? No, it's really close. I got 1.7, and yours actually rounds to 1.9. Did other people get 1.7? Yeah. E negative 5? So the good news, though, is that there is a margin of error on the AP exam for accepted values. They'll track your work and whatnot. Elijah, you are you're good. You're cluster 5C1. I just don't think I ever told you where you're sitting. So, with my weird card stuff that I'm doing. Questions? Want to do one more? A more annoying one? How we usually go. Let's finish up with a final problem. So, just to remind you what the differences have been, there was a problem that gave you an acid and wanted pH. So, those two things lined up nicely. Then we did a problem that wanted pH but gave you a base. So, there was a little extra hiccup where we turned stuff a little more basic so that everything would talk. This final one is what if it gives you K? Now, you probably remember from last unit that when K was given, it was usually bad news in terms of workload. Let's look at this problem. It says find the pH, so we know we're dealing with pH analysis. And then look at that substance, all right? That methylamine is something you're not very familiar with. It also probably isn't jumping out at you as acidic or basic. But here's the trick. If you're unsure of the compound you're looking at, look for nitrogen. If nitrogen is trapped somewhere in the middle, it will line up with your strong and weak rules that nitrogenous bases are weak. If you're having trouble identifying what you're looking at, if it's got nitrogen trapped somewhere in there, then it's going to be a weak base. Also, look at the type of K it gave you. Yeah, I can use that also. KB. Anyway, since it's a weak sample, add it to water in a rice table. So let's take the CH3NH2, CH3NH3, CH3NH3. Keep looking at it, saying it backwards. Add it to water. Bronsted-Lowry, we said it's basic bases except a proton, so it'll become CH3NH3. But also positive. Water is acting as an acid, giving away a proton, leaving him as hydroxide. Fill out the rice table as you know how to do. Ignore the liquid. We have a more exotic starting concentration this time. None of the products. Shift the reactants down. Shift the products up. I plus C equals. The sprinkle this time is K. Unfortunately. So let's start substituting, right? We know that if they give us K, we're not going to be able to start by identifying X. We're just going to have to plug X's into our K expression. So the KB that it gives us is 4.4 E negative 4. 4.4 E negative 4. And now we can set up the rest of the K expression, right? So products over reactants. I'm going to represent the products as X squared, since it's going to be an X times X. You can put the X's in separate brackets if you prefer that. Over the reactant. 0.712 minus that. And here's where we have to have a little talk. Look here. I need you. Have any of you wondered how the quadratic calculator on the internet that I've given you is something that you'll be able to utilize on the AP exam in May? Like, has that bothered you? They're not going to give you internet access the way that I give you on your exams. So how are you supposed to solve true quadratics on the AP exam in May if they don't give you what I gave you? The answer to that question is they're not going to ask you to do that. What I did last unit was I just wanted you to have a well-rounded start to finish view of those types of equilibrium problems because that's good chemistry. College Board doesn't want you to waste time working out quadratics, nor can they give you what I gave you in terms of a tool. So they'll do one of two things. They'll either A, have you stop right before the quadratic. I had you do that in the game we played. Remember Musical Brains? There was a question where you just showed the work at the very end before the quadratic. They could have you do that. Or they'll have you trump X, which is a new thing, trump negative X, that I want to train you how to do. Now, this is easy. This is good news for you because you don't have to do quadratics anymore in this class. I just wanted you to at least see it for a unit. Here's what we're going to do. Look at this. Do you see how we have a minus x as a denominator? That's the key. Listen to it again. Do you see that there is a minus x as a denominator? When that happens from now on in this class, you're allowed to trump it. That means cancel it. And you'll see that when you cancel it, the algebra becomes a lot more straightforward. The reason you can do this is that the quadratic answer versus the one that we're about to get, they're different, but minimally different. So let's just still run through the steps. So here we go. Let's solve for x. All right, if you put that whole number over 1 and cross multiply, 1 times x squared is x squared. And 4.4e negative 4 times 0.712 is that red number. You can verify. How do you isolate x here? It's the square root. The square root key on your calculator is the secondary function of the x squared button. And when you take that square root, you'll find that x equals 0.0177. What is that number? What helpful item does that number represent? The concentration of OH negative. That's where I tend to lose y'all. Is you get there and you don't know why that's useful information. Just track it. X, X, OH minus. And that's what you want, because now you've got yesterday's skills to get to the pH like it wants you to. Couple steps left. This is a strong sample now. That's a strong molarity. All right? Anytime you have a value that's representing hydroxide ion or hydrogen ion, that is strong. And you know what's great about strong in this class? You just have to go negative log of that value. And that'll spit out POH. We can do negative log because it's strong. So negative log of the hydroxide concentration gives me a POH of 1.752. And therefore a pH and final answer of 12.248. Is that what y'all get? Yeah? Any questions? Computer day tomorrow.